So welcome to another Friday folding session. We are here with Jeannie, Shashi, and Peter. Hello and welcome to all the people watching the recording. Rock on. And yeah, I hope you're having a fine day, whatever day it is. And right here, right now, it is 10:31 a.m. And we want to go over the concept we sort of saw last week, which was sort of the circles inside of radial line connections. Well, we want to do that for the case of a 12/8 and the 16/8. And we're going to see how easy it is, and sort of we're going to solve only one triangle, and from there we're either going to cut it or try and work with that. And if we have time, we're also going to do this exercise regarding bouncing and sort of a progression on light bounces, but sort of playing around with something related to Miura, you could say. So okay, so here we go. First step is going to do the 16/8 inside of a silver rhomb, as we call it. And so we start by folding this in half with through the diagonal, like so. And we're not going to cut it the square, rather we're going to turn this over, looking like that. Now we're going to take this long edge and we're going to put it on the fold. What's cool about this is even if you have a A4 paper, this is still, it's kind of necessary, but see, in A4 paper, if you would do this fold, your long edge would actually land on the end of this fold, because an A4 paper is 1 to √2. So because the diagonal of the square is √2 to this 1, then when we fold this on A4, it actually would just cut there. So if you have a letter size you want to turn into A4 ratio, not size, but ratio, that is the point you want to do a perpendicular line on, like that. But if you have an A4, then you would actually find that it meets there. But the rectangle we're getting at actually lands here. So we can activate this fold, and then we can turn it over. And it's easier to see here where our point is. So on that point, we want to do a perpendicular line, perpendicular to this one, parallel to this one. So here on that point, we begin push, 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 push. And then we finally get to where it hits on the point. And what I like to do is I like to push, push, and then hit the point and then sort of hold it. And then I pivot. So I can move this sort of around like this. But when I move this around, that actually is sort of moving from there. So once I have this pivot point located, I can just sort of pivot where I see that over here on my left, it's falling on the edge. That would guarantee perpendicularity. So if you need a little more, you can always push a little further. Just make it as accurate as you possibly can. And that's good enough. You can see mine where it's just going on, and then it hits, and there you go, there you cut. Just as a side note, if you wanted to do a platinum rectangle, you would have to have an angle of pi/6. Here we have pi/12. I think it was pi/6 though. Let's see what we have here. So this is pi/2. This is pi/4. So this is pi/8. So yeah, it is pi/8, this one, this angle. And so if this is pi/8 and this is pi/2, then this would be 3 pi/8. Because 1 plus 3 is 4, and that would complete this satisfaction of the right angle. So for a right angle, we need to get to 4/8 because that's a half. So if this is 1, then these are going to be 3. Side note, right? We're going to cut this away. So I think all but the golden rectangle have this property of just with an angle we can get it. The golden rectangle actually goes, we saw that last time where the golden rectangle actually has, if you do this, it kind of goes a little bit over. But yeah, oh yeah, we're gonna get to the theory of the metallic ratios in a bit. So here we are. And so we have this, so we have it like this. This is the silver rectangle. So there's not debate, but if you go to the origami literature, you actually find the golden, what they call the silver rectangle, silver, not golden, sorry, silver. What they call the silver rectangle is actually an A4 ratio. They call it the silver rectangle, but it's really not. It kind of is, but it's not. To me, this is the true silver rectangle. 1 to 1 plus root 2. So if we actually take like this fold like this, right? If we have that fold, I'm going to fold it backwards just to have it active on the side, just so I don't have to turn it over. But it's the same fold, right? So I have this would be root 2 to this 1. So these two are 1, so it's 1, 1, and here root 2. And I'm saying that the rectangle itself is going to be 1 plus root 2. So because these two are going to be collinear, these values are collinear, I can take the remainder from where that point is and just like spin it. And you can see how it lands exactly on the line. So I can, by congruency, I can sort of demonstrate or show that it is, in fact, this rectangle is 1 plus root 2. And so now just to make it a rhomb, I can take it like an S. So if here I'm raising my bottom left, over here I'm gonna descend my top right. So the intention we're looking for actually will have a 16 at these corners. So we can, if we have a pencil, we can trace that just to be sure. So I'm gonna put in with a pencil line, I'm just gonna put a point here. I'm just gonna put a point here. And I'm gonna do this on mine just to demonstrate. But here we're gonna be a 16. Here's gonna be a 16. Here it's gonna be an 8. And here it's gonna be an 8. So this is kind of relationship we're going for right now. So we already have an 8 division. You can try and sort of ignore these folds. I mean, it helps to sort of leave them folded, if you will. But I'm just going to trace a line just so I can really focus on the rhomb itself and not on the rest of it. Although the rest of it, of course, will inform. We can use it to, to copy whatever it is we find. But we're going to focus on this triangle. Well, not really, but we'll see. So this is an 8-fold as it stands, like this. This could be a octagon. Like this could be an octagon edge and this could be an octagon center. So because we want this to be 16, we need to bisect a little bit more, like one further. So we need to bisect this angle. So we can take either, you can take this angle like this one, this mountain, and we can put that on the line. Again, so we're only gonna focus right now on solving one of them. So we're not gonna bother too much of just going over all of them. Right now, we're just gonna focus on one. Okay, so I have this bisection now. So now this one is properly 16 now because it's bisected. So now we need the sort of the bisection for this, where this one would also sort of be going in that direction. So let's inform this point further. So because we want an 8, and this is already sort of starting to divide into 8, we simply have to, well, we can start with the most basic one, because we already kind of can take that, not for granted, but we can take that, we know this. You can even see if I put my pencil there, you can even see that if we were to copy this angle over here, like the same one, you would get to appreciate how it's almost as if it would also mark the edge of an octagon kind of thing. So on this line, right? So, there's several routes we could take. The one that I would tend to would be first to trace a perpendicular to this line and then just a bisection on it. We can use this to inform further. So on this point, you can simply just take this, fold there. So I'm tracing here a perpendicular line on this point of contact for the 8. Now, it's useful to have this one be a mountain and this one be a valley, because then we can sort of use this to inform the other. So we can tuck it like this, and there's going to be. Because again, we want to copy the same triangle, but now on the other side of this line. This would be almost like a mirror line. So it'd be like we hit, and I could turn it over, but I'm going to keep it on this state, on this side, just for you. But if you want to turn it over, go ahead. But I'm just going to draw a mountain on there. Just really on that line. You can even see how these get arranged. This on the bottom also gets arranged. I am going to turn it over. It's just easier to see. So apparently I might have missed a little bit on that perpendicular line. You can also see that it works like that. That's actually a lot better. And what I mean by a lot better is that you can see that the fold lands precisely on the other one of those things. This was much cooler. So that does away with any inaccuracies I might have done with this tracing, because we have a very clear landing site now. Just put the edge, the short edge of the rectangle, put it on the opposite edge of the rhomb, kind of. Okay. So now we're talking. So now we know where this is going. So on this point, it's going to be the center for a circle. So the circle is going to be located within this triangle. So if we can solve for this triangle, then we can just copy it all around. Now, what's interesting is that it usually, the way that it goes is that in order to go to the next one, so if you picture it like this, the way it's going to go to the next one is sort of going to be by a perpendicular line on the point. Because if we were to replicate the same thing for this, sort of copy the same angle where it goes and it hits on this bisection or whatever, the way that these two would connect would be by a straight line that would actually be perpendicular to this one. So because we have a point and we know where it's going to be perpendicular, you can simply, take advantage of that. So we have the point, we know which line is going to be perpendicular on it. So the fold we're going to do has to go through the point, and this line, because it's sort of our perpendicular reference, is going to fall on itself. So on that point, this line falls on itself. So here I have the line going through the point, falling on itself. Now, we want the same thing, but on the other side. So it's going to go same as a perpendicular, but now toward this edge. But now, so we have, again, a point and where it's going to be perpendicular to. So you can either make this fall on itself, but because this is the longer one, because in this case, our longer is on shorter is on this side. So the shorter is the one you lift. Now, because in this case, the shorter is over here. So it would be that we lift from here down so we can see where it's landing. If we lift from here up, from the bottom to the top, we don't see where it's landing. So we can't appreciate, if we are actually doing the perpendicular thing we set out to do. So this is why we lift the shorter and we put it, so there it is, and there it's falling on itself. So this perpendicular thing applies to all the stars we see, which is crazy, but it does. Okay. So now we have a point of contact. We have 2 points of contact. We know where it's going to be. So this is going to be the radius. From this point to there, that's the radius. So it's going to go, well, it's sort of going to overcast on this, so it won't, so the point where this circle matches on the 16 won't really matter. What matters is toward the 8, because it is our star will match on this point of contact. This point of contact is set, and now it's just a matter of also appreciating that this star has bilateral symmetry. So this is what I call the head. So the line which is going toward the bigger number, in this case we're going towards 16, this would be the head. These are the arms, and these are the feet. I mean, to me, in my imagination, right? And so it's bilateral on this axis. So we have, it would be like, well, so if we oriented like the head up, right? Then these are the left side and this is the right side. So we need, as much as we have a right, we need now a left, we now need a right. So we could use a mirror for this. So we can apply this fold first. And then this is the mirror line. This is line of symmetry. So we can fold on there. Now you can also see how it's actually a line which is perpendicular to the rectangle itself, and it's going through the point. Now this is not always the case, not always the case like in different stars where you have different rectangle kind of thing. But in the case for the 16/8, it just happens to be that way. So now I have sort of my 5 extensions. I have my head, my 2 arms, and my 2 feet for the star. And I have my radius for it. So this is the main reference right here. Another thing is that it's actually going to go, the angle at which this point of contact comes into play is that it's going to be a perpendicular line like this. And it would hit here too. So we can simply just, we can do what we did before, what we've done before, where we can take like a value, sort of in this case would be this value, and we can put that where we want to find the reference to. So in this case, it would be sort of there. And actually, as you do it, you're going to find, that matches perfectly already. So that's beautiful right there. The fact that we have sort of, so then that point is part of the circle. And it's just a matter of finding it on the other side, if you will. And I guess we could mirror this and but again, we could save on time because we know at this point of contact that there's going to be a line which is perpendicular. So we can save on time by knowing that connection. So we simply take that point and just make it a perpendicular. So I'm going to take out a different color because actually this is a pattern line. Everybody clear up to this point? Am I going too fast, too slow? Not clear enough? I'm going to take your silence as an agreement.
Oh no, I spoke all this thing. Mine is mirror image, and I'm getting confused. I don't know what I did. I got distracted in the beginning, and this mirror image.
Yes. Okay. So what you want to do is so you have correct your star symmetry lines. So these lines seem to be correct, like these lines which I've traced here on yours seem to be correct.
Yeah.
So what you want to focus on is where they hit the triangle. So here is where from the center it goes out, and there it hits a triangle on that point. See? So on that point where it hits a triangle, we simply fold a 90 degrees or a perpendicular, to the edge of this paper right there.
Yeah, that I understood, but I'm getting confused because of this mirror image. I mean, your direction and my direction is like mirror image.
Oh, I see. So, if it works like this.
I'm getting confused.
Okay.
If I do it on the other side of the page, it will be okay.
Yeah. Let me trace it on both sides though. So.
Okay, I'll do that with you.
So you just mind that where the center is, and there, so the line which at which it goes toward the edge is a right angle. And you also want this angle of separation there, this right here, to be the same as this one right here. And now here, where it touches the edge of the triangle is where we're going to trace this line. And this line again is a perpendicular. So it's easy to fold in that, this line is just going to fall on itself, or you can be guided by the edges of the rectangle itself. You can even see there that it's sort of going through 2 points of contact of the circle. So far, so good. So because this line is going to be mirrored all around, that's sort of enough information that we can just sort of use this angle of separation as all the information we're going to need. Because here's how. Well, first off, we notice that it's sort of going to be the same angle that goes up as that it goes down. So therefore, we can simply take, there's several ways we can do it, like one way would be to fold on the line of symmetry and then just do a fold with the overlap. Right? There's my line, here's the overlap. That's one way of mirroring, and there it goes. The other way of mirroring is you doing the mirror light trick, where you first fold the line that you want to copy, that you want to mirror, and then you fold the line of mirror. So light beam, mirror line, light line, and then you combine those and you get this, which is pretty much the same thing as the other overlap trick. So it really depends on how you want to approach the problem. But see, what that does is that it copies my angle on both sides.
Ricardo, can you show that second method one more time, please?
Sure thing. So that's what I call the light mirror technique. And that is, first you fold the line of light. So the line of light is the pattern line or the line you want to copy. So in my case, it would be this one, the one I have here sort of partially traced in red. And the mirror line is the line of symmetry. Okay, so first I fold the light line, the pattern line, which I have here, and then you can see that there's my symmetry line, the one that goes toward the center of the circle. And I fold that in an opposite state as the light line. So if my light line is coming in a mountain, then I need my symmetry to move in valley form. So here goes in valley. And then what I would need to fold would be actually this one. This is a folder you wouldn't have. This is a folder you would get. This one that I have here under my thumb right now. So again, there's two ways to do that. So one way is that you first fold the line of symmetry, and then you do an overlap fold on the light line. That's sort of one way of doing it. The other way would be first to fold the light line and then the mirror line, but it produces exactly the same result. You can actually do both and sort of combine them to see, you know, to get some accuracy, and then you can do this thing where you can change up the states of those folds and you can actually get this sort of like crunch on it. Okay. So further, we have some more lines of symmetry here. One of the key ones would be on this line. Let me get another color for this part too. So what I've done here is pretty much, again, from the center line toward the edge of the triangle, I have copied this angle to be the same underneath. So I have an angle that goes on top of it, and then I copy it to be underneath. Further,
Are you drawing on the back? Sorry, are you drawing
oh
on
yeah,
the back?
just the back for me is where I'm sort of going full on both. Actually, I'm going full. I'm just drawing the same thing on both sides. Actually, now that I realize it's just best if I do that. Yeah, I'm drawing it on both sides, just because it might help. But I am just sort of focusing on tracing it within the triangle. Like this triangle is my workspace. Everything else is just sort of superfluous for now. So I see my light line coming in and it hits this line of symmetry. So we could replicate this process. Now we have two ways of mirroring. One is we could fold the mirror line first and then fold the lines we want to copy. It'll be this one and this one. That's one way. The other way, of course, would be first to fold the mirror line, the light line, and then the line of symmetry. You can do both, and the first one would inform sort of a little bit on where it's going to go, and the second one just really drives it home. And here I'm just extending those lines. Sorry for all the changing and turning about, but I'm just extending them.
Where are we making circles? Inside this triangle, or what is the center point of this circle?
Yeah, let me see where my compass is so I can trace the circle. Because we already have enough information to trace that a long time ago, actually. So let me see, where's my compass? Where did I put it? Just a second.
Yeah.
I found it. Here it is. I don't want to damage my table here, so I'm just going to do an improv sort of backdrop for my compass so it doesn't go toward the desk here. Let's see, there we go. Can you see that?
Yeah.
That's a circle. So the radius is from the center towards the perpendicular line.
Okay, thank you.
Yeah, no problem. And so the trick is that once we have we have the line of symmetry here. So the same angle that's hitting on this point is the angle that's going to come toward that point. So we can use the hit on the line of symmetry, that is where the light's sort of hitting on these, and then bounce off from there. I'm just going to go ahead and just inscribe it fully, even though that it's not full, this line. The pattern does not include the full line, but I'm just going to go ahead and just imagine that it's just going through. Just so you guys can also picture how these points are sort of, as they come in, they come out kind of thing. Because if this line comes in, this line goes out. So what that does is that it gives us the same angle here as there is here. Now with that, we now have also information regarding this other point of contact, that is where it hits the circle itself. So we have here a point and we have here the other point. This is the inscribed circle, isn't it? Because it's sort of within the triangle itself. So in this way, again, sort of replicating the jumps of angles. So we have the angle hit here, another triangle. Could it be that it was way out there? I don't think so. It seems a little bit too far. I think this point of contact be the circle. I don't know. Let's try finishing this one. Let's see how this goes, because I'm curious whether I'm actually correct in this approach or not, because it seems to me that I was, but now I'm not so sure. Let's see how this goes. I mean, yes.
Can you hear me?
Yes, I can now.
Okay. It's you drew the right circle but the wrong triangle, so it's okay. So
so is it actually over here, like the center of our circle?
No, the center of the circle is correct. Just the triangle that you drew in with pencil is a little bit too big. So
this one over here.
So these two are correct, but the other one on top is not correct. This one is not. Yeah, that's not correct.
This one over here, like this full.
Yeah, it's too big.
So maybe would this one work better?
Exactly. Yeah, that is. Now it's touching all the sides.
Yeah. Oh, I see what you mean. I see what you mean. Nice. Yeah. Good call. You scared me there for a second. Now. Oh yeah. This makes more sense. Well, yeah. This makes more sense. Isn't that beautiful? Yeah, so it does come in there at the 8 mark, hits exactly on the circle. Ah, that's so nice, so pleasing. I guess we could also bounce this line off. Like we could use this line of symmetry again, and bounce this off down like this. Interestingly enough, here where I bisected just to be safe, just not to be safe, but just because of curiosity and have this point of contact, this would be as though we had a 16 and the 16. So we actually could find the circle within this and try to find another pattern, but it would be more like a 16 coming in contact with a 16. So yeah, ignore this, ignore this. If you ever want to nullify a fold, just simply fold the other way. Okay, so we have the light line that's coming in, hitting on the point of contact with the triangle, which Peter was correct to point out that it's much better to think of it as this triangle rather than the full triangle here. And then we have a line that comes in contact and we know our line of symmetry. So again, we could go two ways of one. I'm gonna start with the first, which is to fold the mirror line first, and then fold the light line, which is gonna be this one, as an overlap. So I hold it in as best as I can, and then do the fold. And then I unfold it. I then fold the light line, then fold the line of symmetry, and then just really try and match it the best I can. So there might be some correction that you could do here, so, you know, take advantage. But I think the previous sort of method, or sort of like doing with the overlap first, just gives you more, I don't know, it gives you an idea of where it's going to go. So it's not as forced as as doing that one first. But now when you extend, you can take into account that this line is going to fall on itself. You can even see that when I fold them together, they sort of come down like this. But again, the purpose is to have the same line, the same angle here. So this is one of the key features of Islamic geometry. One is figures tend to have these sorts of mirror symmetries, like bilateral symmetry to the inside of the skeleton, at least with the stars they do. And also that a pattern line will continue onto a pattern line. A piece rarely, I mean, it's not proper, but you know, you do find this in traditional cases, but I feel that it's not proper for a pattern, for a piece in the pattern to simply stop. And I mean by that the pattern doesn't like keep going after itself. It would be wrong in my field to have like a piece and then something else like jump out in another direction. It does happen that they will make it jump like a little bit, like they'll change the angle just a bit sometimes, but it's wrong when there's nothing even there. That's when it's plainly wrong, when there's nothing after a piece finishing. So it needs to keep going. That's what gives us the illusion, or not the illusion, but the feel of flow. So what makes or breaks a lot of these line patterns. So again, I fold my line of symmetry first. There's a light line that I want to copy. And do that fold just as a bare approximate. And then I fold first my light line, which is the line I just copied. And then I fold my line of symmetry and just make sure that it's proper. Making sure that they connect there. And then I unfold, I fold the line I just got and just make sure that it's properly aligned. And here, what I'm focusing on is that they actually share the same intersection point, because that's sort of where they're going to meet. So it's like this angle is going to be the same on both sides. It's very small now. I'm aware that that might prove a little difficult to see where this is going, but. So yeah, one of the key sort of well, how you say it? It's like a trap. It's that these have a point of contact, like they're not sort of touching one another. They don't go point to point. Rather, there is this point of contact within, but then even that gets ignored because when you draw in fully, like the piece fully, you find that it's the point of contact at it would be I guess the bisection between the skeleton shape. So it does have this, man, I say the same thing over and over. It's like, am I doing it? But yeah, it is a bisection of that angle. It really is. So bisections are one of the key words to all this. I see somebody call this the jellyfish shape, which is interesting. So with this shape done, the rest of it should just fall sort of by itself, if you will. So what do I mean by that? Well, now let's turn our attention toward this part of the triangle. So I guess the reason why I also like decided to inscribe this full triangle is because this triangle is what's getting copied all around. So if we have this triangle, we can just sort of, fill the paper up with this triangle. So if we can completely decorate this triangle, then everything else would just fall by its weight. So this line is a channel line. This line is coming in. So we have a distance for it. We have a first sort of, you can see here almost half of the petal shape. That's after the 8, sort of what's going to be here, but now we're here, so we can see that that's actually sort of copied already. If we had this triangle, this is also something we can complete on. That's interesting. It's interesting the way we could bounce this, man. So interesting. Interesting. Because you could sort of do the same piece here as over here. So sort of actually make it go that way. That'd be weird. I haven't seen that one. But usually the way it goes, and the way we're going to go is that it actually changes direction. So it goes like here and then hits on this point and then goes out toward the other one. So anyway, we're going to use this line of symmetry as a copy. So we have a distance from the petal to the line of symmetry. Here we can see that if we have this as a mountain and here as a valley, you can put them together like this. And then if we do a fold on where this line is, we're copying the distance on the other side. So this is why in AutoCAD, the mirror tool is so useful, because even in origami, the mirror tool is one of the more useful tools we have. The ability to copy a distance, copy an angle, that is key in order to develop these pieces further. You can even see how the line is actually hitting where this line is. It's very interesting. It's going up. And so now what we need is this to be a mirror line. Well, this to be a light line and then to bounce off and then be complete. So we have, again, we have a light line here, a mirror line, sorry, and then we have, this would be the light line we want to copy. So the thing about doing this method is that I think that it can be pretty messy, because if when you're folding this sort of gets misaligned, that misalignment would actually be problematic. So that's why I prefer to fold first. In this case, because it's just so much paper, that's just better to go, like, you got to know when to use the right tool, right? When to use the proper mirroring technique. So because it's so much paper, it would be hard to bounce it properly. I'm using this light line, hits on that point, fold the mirror line, and then bounces back out. And then I can just arrange so that this line is straight and this line falls on itself like this. And then here here's where the alignment comes in, because I have to make sure this line is actually falling perpendicularly on this one. So if I do my mirror trick and that's not aligning, then I have to change it around. And so you can also save on the mirror trick just by having a perpendicular you know you're going towards and the point. So in this case, my point is this contact of this light and this line of symmetry mirror. So it's that point of contact and this one falling on itself. So you can take the mirror trick completely out of context. Not out of context, we completely ignore it if we do it that way. So now we know where this is going up, and where this is going up. So I'm not completely satisfied on this one because I mean, this shape should have the same look on both sides. So it should be like a bilateral kind of symmetry kind of thing. But the way I figure, it seems to me that it's sort of skimmier on one side. And also it should have a point of contact with this line. So like this one we did and the one we just did should be touching at this line. So I'm just gonna go ahead and just make sure that that condition is met.
Could you please repeat the last mirror?
Sure. So even though that I know that this distance has to be copied over here, what also has to happen is that this mirror is going to be bounced off from there. So like this angle, sorry. So that this angle is the same on this side. So these two angles have to be the same, and the distance on this left side where my pencil is has to be the same distance as to here. But, however, they should also be matching on this line of symmetry. So you can see there that it's sort of a little bit slated, like something here is not properly aligning for me. Here I'm combining mirrors. I'm sort of doing a simultaneous mirror for this one. The reason why I sort of changed up my strategy was because I was finding that they weren't actually matching on the line of symmetry. So if I know that I want to force it so that this shape actually does have this bilateral symmetry, that is, has the same distance on both sides, and I know where this 8 is sort of going to match, so I can combine those. I can even see there that this 8, and when I fold this one down on where it's sort of touching, there we go. With all this pencil lines in, sort of like throws me off balance a little bit. I guess that looks better. Here I did just like a pencil line solution where I know it's just going to go from this point of contact toward the other one. And it's going to be all the information that I need. And so I may have gone overboard a little bit on this drawing, like perhaps it's there a little bit. This would go there. Now it's just a matter of finishing this off. And again, because it does have, so wait a minute before I move on forward. You guys having trouble with this part? You guys good so far? Apparently these don't hit, by the way. Like this line of 16 doesn't hit the corner of this petal. Let me see. I don't even know when I stopped recording this thing. I think it was when I went to get my compass. I don't know. Forgot to hit again. So yeah, this was gonna look really weird for the recording, but this is what we get. So yeah, the reason why this might not like tessellate properly is because of this guy. You see there how a corner is sort of exceeded? They actually would solve this just by, just completely having this one go over. Just really just making sure that this guy just went completely over. So then it was when it was next to another one, it just kind of went through, and this one would also be completely extending like so. So when it connects, it would actually be two of these side by side, but only in this case, in the case of this. Apparently, if I put a paper that's white, it'll recover my white balance there. So there we go. So yeah, this freeform cutting actually had its toll on me. It's clearly making this one look wrong. This looks right. This looks right. It's kind of wrong, kind of right. This one looks definitely, I don't know what happened there. This shape also looks not the best. I mean, it's all this overlap and just having like one little bitty triangle be everything. That's a price to pay, this sort of inaccuracies. But that's also why I would suggest if we had more time, I would have done it. Right now, I just got to get going almost. Sorry about that, because I also want to go over a little bit of theory here. And, like this, just put it onto the next one as well. Just like making sure that, what we did on this triangle, just now doing it on this triangle, like on this one. And with this information, like once this one is set in, then it's just easier, a lot easier to just fold onto this. And just we fold onto there. This would fold back onto here. This would fold back. And so it's a lot less stress. A lot less stress if we were to cut on just this triangle. Much less overlap, much less like hurdles and tribulations, just more clean cut. But yeah, this is how you get the 16/8. And so the idea that I've been messing around with is doing the 12/8. with a similar approach, but on a square rather than silver rectangle. The reason why the silver rhomb works is this idea works. Let me just go into the. Let me see here. Give me just a second. Okay. So last time, sorry, I stood up, so I don't know if you guys said anything, but yeah. So last time we talked a little bit about the Schlafly symbols and the way that inside of a triangle there's the pi and all this. So now let's look at the case for the rhombs. So for the substitution rhombs, so let's call them. I call them the families. So the family rhombs, I like to call them. So the way that these work is that a rhomb has mirror symmetry. So it goes a little bit like this. So a rhomb would have one angle here and one angle here. These two angles would be the same, and this angle would be the same. There's only one case where this is not the case, and that's the square where all of them are the same angle. The thing about rhombs is that they always have unit length. So the length of all the edges will always be the same. So there's actually an interesting way that we can approach this problem, in that we can see it for the division that we can add these two, and we would get half a circle. Because if we have, so the formula for the inner, the sum of the inner angle would be n minus 2 times pi. That's the sum of the internal angles. So then this would be, in the case of 4 minus 2 is equal to 2, that's 2, so it's 2 pi. So that's a circle. The circle is also 1 pi, 2 pi. So inside of a square is also a circle. So if we are dividing a circle to get our sense of our pattern, then we can put the same sort of divisions onto a rhomb, because a rhomb is also a 4-sided polygon. So we can put in the divisions we want onto these, and to half of them. So we can imagine that, let's start with the first one that comes up would be on the 4. So the 4 would just have a 1 to 1. So let's do a little list like we did last time. So let's start with the 4. And so the idea is that we start with a 4 family. So then we divide 4 in 2. So we have here n, let's put this list like this. Okay. N and n minus 2. So then we have here 2. So then the next list that we're going to sort of compile, we're going to put it, let me get another piece of paper here. We're trying to find which numbers add up to this number. So which two numbers will add up to this? And these two numbers will represent these two angles. So which two numbers add up to 2? So in the case for 2, we have that it's 1 plus 1. So that's the case, that would be like a square. That would be the saying that this angle and this angle are the same. So we move on. N has to be even, by the way. For this to work, n has to be even. So we now got to 6. So then this would be 3. So then which two numbers add to 3? That's 2 and 1. So it would look like a double equilateral triangle rhomb. It looks a little bit like this. That's saying that this angle is as double as this angle. In the case of the equilateral triangle, that's pretty much the case. We go to 8, and it's 4. Then which two numbers add to 4? Here we have the first time is 2 rhombs. So we have 2 plus 2 and 1 plus 3. And the case is that this, if we sort of proportion them, it's the same as this one. So we're saying that these two angles are the same. That is, that this is sort of a 2 and this would be a 2. Now 2 over what? So the thing is also these represent radians. So this would be saying that it's almost like 2 over 4, 2 pi over 4. Just as much as we can say that this is 2 pi, well, this one would be pi, because it's 1, pi over 3. This would be 2 pi over 3. The same. And this would be pi over 2. So 2 pi over 4 is the same as 2 pi over 2, right? And 1 over 3 would be the rectangle that we just did. This rectangle we just did is this 3 to 1. This is 1 and this is 3. You can even see here that there's 3 petals to an 8. So each petal is contained within 1 radian. 1 radian, 2 radian, 3 radian. And in here we wanted to make it, so this is 2 of 16, and 16 is half of 8, no, double of 8. So that's also why there's 2 petals of 16, where there would only be 1 of 8. So again, this is also why this rectangle would work for applying this. So let's just go up our list until we get to 16. So 10, that's a 5. So which 2 numbers add to 5? That's 1 plus 4 and 2 plus 3. These are going to be the Penrose rhombs. We have a fat and we have a skinny. Penrose, well, not strictly Penrose, but they are the 5-fold rhombs. So this would be a 3 pi over 5 angle, and this would be a 2 pi over 5 angle, just as much as this would be a pi over 5 angle, and a 4 pi over 5 angle. So because this is pi over 5, and so it means that in half a circle, these go 5 times around half a circle. So full circle, this goes 10 times around, right? And this goes 2 times around 5. So if we go full, that's a 10. This one on this angle goes 10 times, 5 times around the circle. All right, let's go ahead. 12 and to 6. So which 2 numbers add to 6? This is the interesting case for the combination. We'll see about that. So which numbers add to 6? That's 1 and 5, 2 and 4, and 3 and 3. So here we have again a square. It's the same for the 2 and 2 and the 1 to 1. And the 2 to 4, if we do this by ratio, we get the 2 to 1. So these two are the same. So we have here a square, a double equilateral triangle, and then a skinny. A skinny that actually would go 12 times around the center. So this angle would be actually pi over 6. This is the sort of the family of it, pi over 6. So it's like this over that, as much as this over that. So this angle would be pi, sub 5 pi over 6. Let's go ahead and move on so we can get to 16. That's a 7. Which 2 numbers add to 7? 1 and 6, 2 and 5, 3 and 4. None of these we've seen before, but these would be the 7-fold rhombs. Finally, we get to 16. Half of it would be 8. So which numbers add to 8? 1 and 7, 2 and 6, 3 and 5, 4 and 4. So here we see we have the 4 and 4, that's a square, and the 2 and 6, that's a 1 plus 3. We can simplify this to 1 plus 3. We have this guy over here. So because these two share the same rhomb, we can use it as a sort of a junction point. We can connect these two by virtue of these rhombs. So I urge you to, you can go deeper and like find different combinations for it. But by using this system, you can actually find the shape that you can put your points in, and just by virtue of connecting different sort of symmetry lines on them, like radial lines that we just did, we can find circles on them. So it's by this virtue that we can also find where the 8 and the 12 can combine for the example I showed you. Because here we have it on this is the 8 and this is the 4, and they share a square. But also the 12 shares a square. So we can put an 8 and a 12 together in a square. We could use tie links, which combine sort of like using those line of symmetry and then just going ahead and sort of find different combinations for it. It would be interesting to see. I haven't tried it myself, but I guess it could be possible, but we would have to see. So this is an interesting little tidbit. I don't know where I stopped the recording. I'm gonna have to go see that. So sorry about where this gets lost, but I guess you see the intention. But right now, we're gonna leave it at that for today. So yeah, I hope you enjoyed it. Hope you learned something. And yeah, anybody's got any questions? Last chance. How's everybody doing? Did everybody get their the 16 though? 16/8. Jeannie, Shashi, Peter.
I'm working on it.
Also working on it.
So this to me is one of the more fascinating aspects of like the crystallography, at least, like finding these rhombs and like these shapes, and then going about like finding their numbers and then finding the rhombs. So these are all rhombs, the angle, the edge length, And then what's interesting is that you can use Islamic patterns to decorate. You can decorate these with Islamic patterns, and then the decoration can serve as a substitution matching rule. So that is to say, the pattern of the rhombs might continue with you using an Islamic pattern as a decoration. So here we have, for instance, we have the silver rectangle, but we also have like a quarter of a square here. So we could apply now a square to this part. So if we had the same thing, let me actually get the other one I have to show you.
See, if we tessellate this pattern, then we will get the same. Can you hear me?
Yeah, I can hear you.
Okay.
You can see there.
So if we, yeah.
This one I actually did on, it turns out I only did, again, half of it. I think I actually did copy folds onto this one and then cut there. I'm not sure actually now that I'm looking at it. But from here you can see how, yeah?
Yeah.
Sorry.
See, if we tessellate this pattern, then we will get the same pattern which we did last time, maybe last to last time. Or maybe this is that pattern which Peter did, and then I copied his pattern.
Difference for this one, the crucial difference for this one is this solution over here. So you see how these sort of are crashing? So this is like the key difference for this, in the case for this sort of thing, that if we were to actually tessellate it, we would produce, so we have two silver rhombs next to each other, and so by elimination we would have here a square. So that's the space between. We can actually solve for how many petals there are here, but then if we were to copy this to the right, you could see almost like where this right angle would sort of be produced, almost sort of here. So the case is that this shape turns out to be the weirder one, but we could just sort of imagine that it's sort of going to copy this from over to here, and then it's this shape that becomes the problem. But we could, as I did, sort of just completely extend and just connect there, and just this one also just extend and connect there. But this is a weird one. This is a weird sort of solution. But yeah, usually the way that that you do it for this pattern is not to solve inside of a silver rhomb, but rather to solve for it inside of a square, which these also have. So the square is in the 8 and the 16, but so is this rhomb, the 1, 2, the 2 to 1, 2 to 6. No, 3 to 1, 2 to 6 is the same one over here as it is over here, and just as much as the square is the same one. So we can put this division inside of the 16 inside of a square as much as we can put inside of this rhomb. So that's why it works.
Ricardo?
Yes.
There would just be another star shape if you wanted to solve for the connection of two, I forgot what it is, 16s, let's say.
Yeah.
So that has to be another shape by construction there in the corner. Right?
Yeah, definitely. You could just keep like extending these, for instance. And they would hit, I feel, in a similar way that this one hits, because it's the same sort of line symmetry. The problem, I think, would be just the point, but as you say, I mean, it would be constructible. But it's interesting that it's sort of not by mirroring that we would get this one, rather it's its own thing that, you know, deserves its own sort of that space. You can see this one is a little more clear in this construction, a little cleaner on this. Yeah. So today we're going to leave it at that. I want to thank you very much for joining us.
See, this is quite similar to this.
Oh, let's see. To this 16/8, that one?
I don't know, 16/8 or what. This is it.
It's very beautiful. That's
Thanks.
It's a
yeah.
Yeah, this is the one. Yeah, this is the one which you did.
Nice.
I'm talking about this one.
Yeah, so I think it's a little bit different because the pentagon doesn't tile the plane, so there are some shapes in between that you have to put.
Although I
yeah.
feel that for that one, you could actually find this rhomb by connecting the certain centers. And this rhomb you could sort of tessellate. I feel maybe that could be, maybe that could be an approach.
I think this is one of the Penrose tiles already for this kind of fivefold symmetry, and that
Yeah, the
doesn't
thing
tile.
is, like, the Penrose tiles are not the rhombs themselves. The Penrose tiles have instructions onto them on how to tile them. So they actually have points and arrows. So if
but
the
only,
rhomb doesn't have a point or an arrow, it's not a Penrose. But it is, like, it's the foundation for it.
I mean, the tiles are the same. It's only if you want to have a quasi-periodic tiling, then you have to follow this kind of rule. Otherwise, you can do symmetric patterns too. That's
No, but what I mean is
possible.
that, like, technically, it's a
Yeah,
Penrose
I know.
rhomb if it has the decoration, like a specific quasi-crystal, as you say, like. But I mean, it's probably like a moot point, but it's sort of like a technicality, because these rhombs have been used since antiquity. But it's what makes it a Penrose is the way that he decorates them with the arrows and the points with color and whatnot. But yeah. Yeah, I hope you guys enjoyed this. Hope you guys had fun.
Yeah. Thank
Yeah, I
you.
had a great time, Ricardo. My brain is really, really, really full.
Nice.
So, as it always is at the end. So thank you so much.
Yeah, no
Thank
problem.
you. Thank you. Bye.
Thank you,
Bye.
Shashi. Thank you,
See
Peter.
you next
Thank you,
week.
Jean.
Bye.
See you next week. Yeah.
Thank you.
Yeah,
Bye-bye.
bye.
Thank you, Peter. Thank you, Jeannie.
Thank you.